It gives me pleasure to introduce Nobel laureate for the discovery of plutonium and other elements, the scientist who arranged the periodic table in its modern form, that is today's form, the name behind element 106, my colleague and friend of 25 years, Professor Glenn Seaborg.
All right. Thank you very much. As you may have gathered by seeing the slide, I'm going to talk about the elements that have been discovered here at Berkeley. And actually, I'm not going to say anything about the two lighter ones there. I'm going to talk about the transuranium elements, the elements with the atomic number greater than that of uranium, which is 92. I notice that the periodic table over here is all out of date, and but I have here a periodic table tie that I can use in case I forget, how these elements fit in. Actually, I'm going to use the periodic table a good deal, and begin with a periodic table as it appeared before World War II. Actually, the way it appeared in 1934 when I came to Berkeley as a graduate student. By that time, the neutron had been discovered, and it looked like it would be possible to bombard uranium with neutrons in order to get up to higher atomic numbers, the transuranium elements. Safer that way. And the periodic table at that time had the elements uranium, thorium, protactinium, and uranium up in the body of the periodic table. And so it was natural to predict that the elements beyond uranium, the transuranium elements, the elements with the atomic numbers 93, 94, 95, and so forth, would fall in the periodic table in this way. And thus 93 would be under rhenium, it'd be chemically like rhenium, ecuranium, 94 would be like osmium, and so forth. And it was on this basis that we made the predictions of the chemical properties so that we could go on and synthesize and identify these elements. In order to do that, of course, we had to know their chemical properties so we could make the separation from all of the other activities that were present. So on that basis, experiments were done in Italy in 1934 by Fermi and co-workers, and they thought they had produced, by bombarding uranium with neutrons, they thought they had produced these elements with the higher atomic numbers, transuranium elements. For example, the 13-minute activity seemed to be chemically like rhenium, ecuranium. And this work was actually carried on in Germany by Hahn, Meitner, and Strassmann. And they found a number of activities that seemed to have the chemical properties of the, as predicted by the periodic table of that time, ecuranium, osmium, iridium, and so forth. And they studied these for a number of years until in 1938 they found that the element, that one of the elements actually had a atomic number down in the middle of the periodic table, and that what had actually taken place was nuclear fission. The uranium had been split in half. And then they found that all of these activities that had been assigned to the transuranium elements were actually due to fission products. And we were back to square one. There were no transuranium elements at all. They were all fission products. And here's a picture of Strassman and Meitner and Hahn taken a few years later. Let's see. Then in 1940, McMillan and Abelson here at Berkeley, where we had a much more intense source of neutrons using the 60 cyclotron, bombarded uranium with neutrons, and they found the first real transuranium element with the atomic number 93, uranium-238 capturing a neutron to give uranium-239 and emitting an electron to give the 93-239. And they found that it was an electron emitter, a negative beta particle emitter, but they couldn't find the daughter, which was expected to be an alpha particle emitter, because its half-life was too long. It just didn't decay fast enough so that you could detect the alpha particles. And they found, furthermore, that the 93 was chemically like uranium and not like rhenium, as the first periodic table that I showed would have predicted. And here's a picture of McMillan taken at about that time, June of 1940. A picture of Abelson taken at that time. This is when I entered the picture. McMillan had started a different approach to try to find another isotope of element 93 that, when it decayed, would give a detectable alpha radiation in the daughter. And we bombarded the first bombardment on December 14th, 1940, uranium with deuterons, and we found another isotope, 93-238, which, when it decayed, led to a detectable amount of alpha radioactivity. We could actually estimate the half-life from the intensity of its radioactivity and the intensity of the radioactivity of the parent. And we made a chemical identification of this on February 23rd, 1941, which is the date that really denotes the discovery of the element with the atomic number 94. And we estimated the half-life as 50 years. And here's a picture of me taken at that time. And I like to show it to indicate how little I've changed in the last 55 years. And here's a picture of Kennedy. Actually, we went down to, on the Christmas Day of 1940, we went down to my parents' home in Southgate, near Los Angeles, to spend the Christmas holidays. This picture was taken on December 25th, 1940, in my parents' backyard. And we left our student, Arthur Wall, who was my graduate student at that time, at Berkeley to work over the Christmas holidays. Then we, as the discoverers of the element with the atomic number 94, we had the privilege of suggesting a name. And since uranium had been named after the planet Uranus, and Neptunian named after the planet Neptune, for a while we thought we'd reached the top, that we should name it extremium or ultimium. Think how foolish we would have been. We finally decided to name it after the next planet that fortunately was another planet, Pluto. And we probably should have named it Plutium. But we like plutonium better, plutonium. And we obviously should have given it the symbol PL, but we like PU better. so we gave it the symbol PU. And this work was our own research. It was not sponsored by the federal government, and we kept it secret voluntarily, you'll see why in a moment. But we wrote a report, and in that report, which we sent to Washington in 1942, we actually it was actually published after the war in the Journal of the American Chemical Society, and here is a reproduction showing the exact wording where we made the suggestions for the name plutonium and the symbol Pu. And I had the privilege of meeting Clyde Tombaugh, the discoverer of the planet Pluto, in June of 1991 on a visit to Albuquerque. It turned out that he was only 24 years old in 1930 when he discovered Pluto, so he was still alive in 1991. And I dictated the reports that we sent to Washington announcing these discoveries to a girl named Helen Griggs, who was the secretary of Ernest Lawrence, the inventor of the cyclotron and the director of what was called the radiation lab then. It's the Lawrence Berkeley National Lab now. And she was so efficient in typing these reports that I began to date her. She doesn't like that characterization, and I must admit she had other qualities. And here we are on the street of on the sidewalk in San Francisco on Market Street on Christmas Day 1941. And this picture was taken by an itinerant photographer who just snapped our picture and gave me a card, and I could send in 50 cents and get a copy of the picture. And on the 25th anniversary, it'd be February 1966, the room in Gilman Hall where plutonium was discovered, where the oxidation was made on February 23rd, 1941, that led to its discovery. This room was declared a historic national landmark. And here are the people involved at that time: myself and Art Wall and Ed McMillan and people from the Department of Interior. And by the way, the room is still there. The building, Gilman Hall, is still there. It's the only one of the original chemistry buildings. And if you want to go up, you can see room 307 as a landmark. And just a week ago, the whole building was declared a National Historic Chemistry landmark because of the discovery of plutonium there and the other early work done by Gilbert N. Lewis and so forth in that building. Then we went on, joined by Emilio Segre, and bombarded a lot of uranium for a long time and produced a detectable amount of the daughter, plutonium-239, a half a microgram. And we could deduce from the intensity of its radioactivity and the intensity of the radioactivity of its parent, its half-life as 30,000 years. And that was not a bad value because its present day, the best value is 24,000 years. It just showed that we had so many errors that they canceled each other and we came out with a good answer. But we went on with that, and using the 37-inch cyclotron in the neighboring building, we bombarded this a half a microgram of plutonium-239 with neutrons and compared its fission with uranium-235, the famous fissionable isotope of uranium, of natural uranium, using natural uranium in the experiment, and found that it was fissionable with slow neutrons with a probability even greater than that of U-235, a cross-section even greater than that of U-235, which meant that it was eligible to be the explosive ingredient of an atomic bomb. And that's why we kept it secret voluntarily. And this led to the setup of the Manhattan Project, the plutonium part of the Manhattan Project. And here is the sample in the cigar box in which I preserved it during the intervening 25 years. And on the 25th anniversary, the fission was measured on March 28, 1941, and on the 25th anniversary, on March 28, 1966, we presented this to the Smithsonian Institution, where it's now on display in the Science in American Life exhibit in the Museum of American History of the Smithsonian, if you want to see it. And it's in that cigar box that I put it, one of G.N. Lewis's cigar boxes that I inherited when I served as his assistant, my first job after I got my PhD. And here's the campus at about that time. Here are the chemistry buildings, chemistry and the radiation the laboratory and so forth. Here's Telegraph Avenue and Bancroft Way. Here's the area where Sproul Hall now is, and here's the area where the Student Union is now. At that time, they were just commercial establishments. And here is the building, the Krautker Laboratory, where the 60 in cyclotron was situated. It's almost just about where this building is, just a little bit over on that side. And here is the other building, the old radiation laboratory, where the 37 in cyclotron was situated. Now, when the project then was centered at the University of Chicago, the so-called metallurgical laboratory, and I was called there to work out the chemical processes for the separation of plutonium as it would be produced in quantity in the reactor at Hanford. And I wasn't about to leave Helen Griggs here, so alone. So I proposed to her, and she accepted me. I arrived in Chicago to work on this project on April 19th, 1942, my 30th birthday. Those of you who are good in arithmetic can calculate how old I am now. And I came back and picked up Helen. We went down to Southgate and visit my parents' home, and then the next day got married on the way in Nevada on the way back to Chicago. In Chicago, we had to work out the chemical process and the chemical properties of plutonium using ponderable amounts, weighable amounts, visible amounts. Everything we'd done so far was done with just tracer amounts. But we had to have the same concentrations that would exist at Hanford. So I had the idea that if we could produce, by bombarding a lot of uranium with neutrons from cyclotrons in a long time, we could produce micrograms of uranium. And if we would dissolve that in microliters, we'd have grams per liter, which would be the concentration at Hanford. The only thing is, how can we had to solve the problem of working with microliters of solution, and this was the field of ultramicrochemistry. And I heard about this and learned about the availability of two ultra microchemists here at Berkeley, shown in this picture, Burris Cunningham and Louis Werner, and I hired them and brought them back to Chicago to work on this ultra microchemical scale. Here they are in the room 405, Jones Laboratory, at the Metallurgical Laboratory of the University of Chicago, on the day that they had isolated visible amount, a microgram of plutonium hydroxide on August 20th, 1942. And here I am at the same time in that laboratory, which was also declared a historic national landmark on the 25th anniversary of this first wing of plutonium, which was 2.77 micrograms of the oxide, weighed on September 10th, 1942. With this balance, a quartz fiber, a balance made out of quartz fibers that you could barely see, and then by calibrating it, you could see how far the quartz fiber was depressed as you put weight on the weighing pan. And as I like to say, we were weighing invisible samples with an invisible balance, but it was possible to weigh them with an accuracy of about 1%. And here is that first plutonium weighed on September 10th, 1942, here on this platinum holding device, background, and here is the forceps holding no, it's the other way around. There's the forceps holding the platinum weighing boat. And this sample is now preserved and is on display in the Lawrence Memorial Room of the Lawrence Hall of Science here on campus. Then we got to the point where I could have some of the people working on the problem of trying to find the next two elements, and we thought that we had solved the problem of how to predict the chemical properties, because, as I told you, the chemical properties of neptunium and plutonium are like uranium. So we predicted that there'd be another inner transition series of sort of like the rare earths, where we have the 14 lanthanide elements following lanthanum, where the inner electron is being filled, shell being filled, the 4F. I thought there would be 14 5F shells here, 5F electrons, and that elements 95 and 96 would be chemically like uranium. And when we tried this, we couldn't find any evidence for elements 95 and 96, and the reason for that was we were predicting the wrong chemistry. Actually, we were throwing the samples, the fractions that had elements 95 and 96, down the sink because we still had the wrong form of the periodic table. I like to make the point that we were slow learners. And then I got the idea in 1944 that the periodic table was probably wrong, and that we should move these elements here that had been up here down here and begin the actinide series, clear back here at thorium, and with that element 95 would be like europium and element 96 would be like gadolinium. This would be an actinide series, and when we used that, we found that we could make the chemical identification and discover the elements with the atomic numbers 95 and 96. This is the periodic table I published in the Chemical and Engineering News in December of 1945. I showed it to a number of my friends, actually the leading inorganic chemists in the world, and they told me not to publish it. You know, I was just a brash young chemist, and it was wrong. I shouldn't do this. It would ruin my scientific reputation. And I didn't have any scientific reputation, so I published it, and this concept led to my receiving the Nobel Prize. And I like to tell that story because it shows how easy it is to get a Nobel Prize. Right? And the announcement of the discovery of these next two elements was made in a rather unusual way. I appeared as a guest on what they call the Quiz Kids program. This was a national radio program every Sunday night, and I appeared on Sunday, November 11th, Armistice Day, 1945. And in this, the radio audience would send in questions to the panel of kids aged 5 to 15, and the one who answered the question first would win a war bond or something. And they turned the program around, and in the last half of the program, kids asked me questions. And one of them asked if there had been any elements discovered at the metallurgical laboratory during the war, and I blurted out yes, 95 and 96, and that was the announcement to the world of the discovery of these elements. And that program was recorded on an old 78 RPM disc that evening, and a copy was sent to me, and I've had it transferred to a cassette tape, and now you can hear it exactly as it went out over the air on November 11th, 1945. Oh, I should have said that my co-discoverers of elements 95 and 96 were Albert Gyorso, a picture here, who has been my co-worker ever since, and two young bachelor degree chemists, Ralph James and Tom Morgan.
Children, we have the great honor to present as our guest observer on this Armistice Day program a most distinguished scientist, Dr. Glenn T. Seaborg. Dr. Seaborg was a co-discoverer of the new element plutonium at the University of California, and he was closely concerned with the development of the atomic bomb at the University of Chicago. Because the whole world is rightfully curious about the atomic bomb and its grave implications for world peace or world annihilation, it seems a very appropriate subject for our Armistice Day discussion. We're going to reverse roles in our final question session to let you children quiz Dr. Seaborg on the atomic bomb. I hope you'll have some good, solid questions ready for them. Now, let's get roll call started. Harvey?
I'm Harvey Bennett Fishman. I'm 15 years old, and I'm a sophomore at the South Shore High School in Chicago. Well, Doctor, do you really think they'll be able to harness the energy of the atom and use it for driving ships or planes in the post-war world?
Well, Harvey, yes. I think they will. Not right away, but sometime in the future, say 10 or 15 years.
Richard, how about your question?
Well, Doctor, how long do you think it'll be before some of the more stable elements will be split, that is, on a practical scale?
Oh, on a practical scale. They've been split on a small scale. On a practical scale, I don't know. A new principle would have to be discovered, or a new type of reaction. However, I wouldn't say that it'd be impossible, maybe in 50 years or so.
Well, another thing,
Here it is.
have there been any other new elements discovered, like plutonium and neptunium?
Oh, yes, Dick. Recently, there have been two new elements discovered, elements with atomic number 95 and 96, out at the metallurgical laboratory here in Chicago. So now you'll have to tell your teachers that to change the 92 elements in your school books to 96 elements.
That we didn't have Dr. Seaborg at the microphone for the entire half hour. We certainly thank you, Dr. Seaborg, for taking time from your many pressing commitments to be with us tonight. This is Joe Kelly dismissing the Quiz Kids class until the same time next Sunday when we'll broadcast from Youngstown. Good night, kids.
Good night, Mr. Kelly.
Listen to the Quiz Kids every Sunday, and listen to your old friends Lum and Abner every Monday through Thursday. Folks, check your family supply of Alka-Seltzer. And remember, when your tablets get down to 4, that's the time to buy some more. This is Bob Murphy speaking.
Then we went on, and as the slide that you just saw, bombarded plutonium-239 with neutrons to produce heavier and heavier isotopes after we'd returned to Berkeley, and used these to identify through synthesis reactions the heavier and heavier transuranium elements. And first of all, we used, up until 1956, just light particles as the projectiles in the bombardments, neutrons and protons and deuterons and helium ions. And then in 1956, we received the funding to build a heavy ion linear accelerator that would accelerate still heavy ions of carbon and nitrogen and oxygen and so forth, so we could get up higher and higher in the periodic table. And in order to do that, we needed to bring this tank up the hill for the heavy ion linear accelerator. And here we have the dilemma of this tank coming up the hill through this hairpin turn, this tank weighing 50 or 100 tons, which we were afraid might roll down on the campus in the city of Berkeley. And in order to be sure that that didn't happen, we tied it with this rope here to that tree up at that point there. Well, using this accelerator, we produced a number of elements. I'm mentioning this one in particular, element 106, oxygen on californium, 8 plus 98 makes 106. We had a lot of our friends check to be sure that was correct, and identified through its decay by alpha emission to previously known daughter and granddaughter. And this work was done by this group here of 8 people, and there was a great deal of controversy over naming this because there was some competing claims for its discovery. And finally, one member of our team, Albert Chioso, decided it should be named after me, Seaborgium. And then the trouble began, because the Commission on Nomenclature of Inorganic Chemistry of the International Union of Pure and Applied Chemistry, I think I got all that straight, they rejected the name because I was still alive, and by God, they could prove it. So this led to a lot of back and forth. They finally found that their own bylaws suggested they should go out for comments to the scientific community, and they went out all over the world for comments, and the answers came back overwhelmingly that it's all right to be alive. And so they finally reversed themselves, and in a vote on August 30th of this year, they adopted the name Seaborgium. And so now we have the name Seaborgium on the periodic table. Now, here's where we stand today then. There are actually 20 transuranium elements found, the last 6 actually in a laboratory in Germany, except that we have some competing claims for here at Berkeley of the discovery of element 110 that hasn't been named yet. The last 3 haven't been named yet. And there's also, and here's a summary of the situation. Elements 93 to 112 have been discovered, and there's also the hope that we could find elements up or still higher, because there's the thought that there might be some closed shells of increased stability up around element 114, just like there are closed shells for the noble gases of 6 electrons that leads to increased stability. There are closed shells of protons and neutrons, and there's a prediction that there should be a closed shell around of 114 protons, and we're trying to make with some spread in the stability, and these are called magic numbers, and we're trying to reach that island of stability, and actually there will be experiments here by our group next year to try to make elements 113 and 114, although there are other 2 laboratories too that are going to try to beat us to it at that time. Here then is the form in which we have the periodic table today. After you finish the actinide series at element 103, you go back up into the main body of the periodic table and have Rutherfordium at element 104, and so forth, up to 112, these 3 not named, and then we know with full confidence that the next elements will fit in up to element 118, which would be the next noble gas. I believe that it'll be possible to produce another half dozen or so elements and get up to about element 118. But when I say we, I mean you, somebody in the future that enters this field. It'll probably take a number of years, but I think we will be able to get up a little further. And here's a periodic table that goes up even further. I think just like there are 14 4f electrons here in the lanthanide series, there are 14 5f electrons here in the actinide series. There should be 14 6f electrons and 18 5g electrons in another inner transition series, which I've named the superactinide series. And then you get back up into the body of the periodic table and go on up to element 168, which would be the next noble gas, actually a noble liquid, because its boiling point would be above room temperature. However, there's no chance really of seeing elements this heavy because the half-lives are too short, and there are no reactions for reaching these high atomic numbers. But as I say, I think it will be possible to go up maybe another half dozen or so atomic numbers, 118 or 120. Actually, in the past when I made predictions, I've always been too conservative, and we've actually done a little better than I had predicted. Now I'm going on to another phase of my career, which sort of shows what can happen to a fellow if he lets his guard down. I've been an advisor to the last 10 or 11 presidents of the United States, as listed here on this slide. Beginning, of course, with Franklin Roosevelt, for whom I worked on the atomic bomb project. I've met all of the presidents since Franklin Roosevelt. I didn't meet him, and I have pictures with all of the presidents. Actually, however, my wife Helen and I, while we were living in Chicago, saw Franklin Roosevelt when he came to Soldier Field to campaign for his election to a 4th term. And here at the end of October of 1944 is a picture of Franklin Roosevelt at Soldier Field, and Helen and I are up here in this. Also in 1944, in July, we were listening on the radio, and we heard the Democratic Party's convention was being held at the convention center in the stockyards, and we heard that the vice president was being nominated, Harry Truman, and we got on the streetcar and went down to the convention center and walked right in and found a place right over here and stood watching as he was making his acceptance speech. Then, actually, I served as a member of the General Advisory Committee of the, appointed by President Truman to the first General Advisory Committee of the Atomic Energy Commission. Then I was appointed a member of the first President's Science Advisory. That's better. That's the right one. I was appointed a member of the first President's Science Advisory Committee, and yeah, right here. Oh, here we are. Yeah. The PSAC, President's Science Advisory Committee, appointed by President Eisenhower, and here we are meeting with the President, and there's President Eisenhower, and here am I in the back row. I don't know why they put me in the back row in these pictures. Then I was appointed as the chairman of the Atomic Energy Commission by President Kennedy. I got a call in January of 1961 from the president-elect. I was serving as the chancellor of the Berkeley campus then, but spending time up at the radiation laboratory, the Lawrence Berkeley lab, a condition under which I'd accepted the chancellorship. Somebody came up and said, President-elect Kennedy wants to talk to you. He came on the phone and he invited me to be chairman of the Atomic Energy Commission, the predecessor of the Department of Energy in his administration. I said, gee whiz, how long do I have to make up my mind? He said, take your time. You don't have to let me know till tomorrow morning. I went home that night and I put the question to Helen, and by that time we had 6 kids. And they rebelled. They didn't want to go to Washington. And they demanded a vote. And I said, all right, you can vote. They voted 7-1 against going to Washington. And I exercised the power of the head of a Democratic household, and I vetoed the vote, and we went to Washington. And here I am briefing Kennedy on atomic structure and nuclear structure and so forth. He was a very apt pupil, actually better than some of the other presidents that I'd met. I was asked to stay on under President Johnson, and here I am one afternoon when I was called to the White House to talk with him. And it turned out that he didn't have any particular agenda on his mind. He was just lonesome, and he kind of liked me, and we spent the whole afternoon just sort of chewing the fat. Then I was I was asked to stay on by President Nixon. I was about the only high-level member of the previous two Democratic administrations that was asked to stay on by President Nixon in the Republican administration. I had actually met him in 1948 when we were among the 10 outstanding young men of the year of the Junior Chamber of Commerce. However, as time went on, I didn't get along so well with the Nixon crowd, John Mitchell and so forth, and they wanted me actually to do things that I thought were unethical, and I finally left in 1971. However, I did convince him to give Atomic Pioneer Awards to General Leslie R. Groves, the head of the Manhattan Project, and Vannevar Bush and James Conant, the scientists who led the scientific work in World War II. I knew Jerry Ford when he was the minority leader in the House. Here I am introducing him at a meeting of the World Future Society in April of 1974, just 4 months before he became president upon the resignation of President Nixon in August of 1974. I remember one occasion when we were at a banquet sitting at the head table, realizing that it was the night of the finals of the NCAA basketball tournament, and we went up to a room and watched this on TV. His alma mater, the University of Michigan, was playing my alma mater, UCLA. UCLA had no trouble beating them, you know, and poor Jerry Ford was very unhappy, but I tried to console him, and then we went back down and took our places at the head table, and nobody had missed us while we were gone. I knew Jimmy Carter, Jimmy Carter, and here is one occasion when I met him at the American Academy of Achievement banquet in Minneapolis, and this is Ted Turner of CNN. I was appointed by President Reagan to the National Commission on Excellence in Education. They came out with the famous report, A Nation at Risk, and here I am with the report with President Reagan. And I know I shouldn't say this, but I'm not sure that he knew what we were talking about. I was called to Washington to brief President Bush on cold fusion. I don't know whether you know what cold fusion is, but it's very cold. It didn't work. And I didn't know quite what to say, but I told him that I didn't think it was valid and that he should appoint a high-level panel to study it for 6 months, and they'd come out with that same conclusion. And he did that, and they studied it for 6 months and came out with the conclusion that it wasn't valid. It was on this occasion, this very week, that Barbara Bush had been treated with radioactive iodine-131 for her Graves' disease, which put it under control. And I told him casually that I was the discoverer of iodine-131, which helped capture his attention. He said that, you know, that Barbara is radioactive and at the thyroid, and the doctor told her not to kiss the dog because of the radiation, you know, but he didn't say anything about me. And then I actually went to the White House with the 40 winners of the Science Talent Search, run by Science Service, of which I was serving as chairman. And we met with President Clinton. Guess where I am? Right there. And then I saw him afterwards, and he'd also been asked about cold fusion, so I told him it was very cold. And I also met Al Gore on that occasion. I had met him when he was a teenager. Actually, his father, Al Gore Sr., was a member of the Joint Committee on Atomic Energy when I was chairman of the Atomic Energy Commission. And I, of course, had to meet with the Joint Committee on Atomic Energy many times, and I met young Al Gore in the Gore home. And then finally, this is my last slide.
Your timing and everything. Brilliant.
Yeah, that's right. Right.